Hello again, this is Professor Roman. Let's continue the lecture series Transition to Advanced Mathematics. We're going to talk now about binary relations. Relations between objects are prevalent in mathematics. You should already be familiar with several of them. Here's a short list. Equality, of course. Less than or equal to, less than, greater than or equal to, and greater than on sets of numbers. Logical equivalence is a relation on the well-formed formulas in the propositional calculus. Set inclusion and strict inclusion are relations on families of sets. Divisibility is a relation on the integers. The same size relation exists on finite sets, even on infinite sets. In this chapter, we will discuss the mathematical concept of a binary relation. There are actually two common and closely related variations on the definition of a binary relation. That's a bit unfortunate, but we're stuck with it. Here's one definition that you will see in many books. Let A and B be sets. A binary relation from A to B is a subset R of the Cartesian product, A cross B. That means it's a collection of ordered pairs, where the first component comes from A and the second component comes from B. The domain of a relation is the set of all first components. So formally it would look like this: the set of all little a in capital A such that there exists a little b in capital B for which the ordered pair AB is in the relation. The range of R is the set of second components, which looks like this. A binary relation from a set A to itself is generally referred to as a binary relation on A, and A is called the underlying set for the relation. I'm going to sometimes just use the term relation, and when I do that I'm talking about binary relations. There are other kinds of relations, and I'll mention them briefly later. But the focus of this chapter is almost exclusively on binary relations, so I may just refer to them as relations. This definition of a binary relation does raise a slight issue. Namely, when are two binary relations equal? And there are two possibilities here, depending on whether or not the sets A and B have to be the same for both relations. So just to illustrate what I'm saying, let's consider two relations here. This is a relation from A to B. A is the set 1, 2, 3, B is the set 4, 5, 6, and R is the relation that consists of a single ordered pair, 1, 4. So 1 is related to 4, and that's it. I can change the sets A and B, A to A prime, which is 1, 2, and B prime, which is just the set containing 4, but leave the relation, the set of ordered pairs itself, alone. So again, it's just the single ordered pair 1, 4. So the question is, should these be considered the same relation because they're the same set of ordered pairs, or different relations because the sets A and B are different? Well, that's a question, and for us, we're going to consider these two relations as the same. So all that matters are the ordered pairs in the relation, and not the sets A and B. I can't say that everyone takes that point of view, so I obviously don't know what everyone does. But the alternative definition of binary relation that is found in a great many books on set theory, and so to me that would seem to be the highest authority, makes no mention of the sets A and B, and so avoids the equality issue that we've been discussing. Here's the formal definition. A binary relation R is a set of ordered pairs. That's really the end of the definition, but I've elaborated a little more here. That is a subset of the class sets cross sets. In other words, it's a subset, not a class, but a subset of this class of all ordered pairs of sets. We've discussed the fact that all sets thrown together don't form a set because of the Russell paradox. They form a class. Similarly, ordered pairs of sets are not going to form a set. But the main point here is that a binary relation is just a set of ordered pairs. The domain of the relation is the set of all first components of the ordered pairs, just as it is in the previous case, and similarly for the range. So those are not affected by the different definitions. I added one more definition here that I don't think we're going to use too much, if at all, but I thought you should at least see it, because you'll probably may see it elsewhere. The union of the domain and range of a relation is called the field of the relation. Now these two definitions are not exactly the same, but if R is a binary relation under the first definition, therefore it's a binary relation from a set A to a set B, then it's also a set of ordered pairs, so it fits the requirements of definition 2. And conversely, if R is a binary relation under our second definition, then we can always set A to be the domain of R and B to be the range of R, in which case R now is a subset of A cross B, and so it's a relation from A to B under the first definition. So we can go back and forth between the two definitions. They're different, but they're not horribly different, so it's not something to be overly concerned about. If R is a binary relation, and if an ordered pair AB is in R, we say that A is related to B. But some care has to be taken with the language. For example, it would not be correct to say A and B are related just because AB is in R. The problem is we don't know whether the ordered pair BA is also in R. To say A and B are related sounds very symmetric, and we don't necessarily have symmetry. We'll talk about symmetry later. So it's important to use the precise language here. A is related to B, which is not the same as B is related to A. That's why we use ordered pairs to define relations and not unordered pairs. Now we have to speak about notation. Mathematicians will often write ARB in place of ordered pair AB is in R, and then AR with a line through it B in place of ordered pair AB is not in R. This is very common. Nevertheless, both notations do have their place, and so you will see them both. Next thing to note is that most commonly occurring binary relations, such as equality, less than or equal to, subset, divisibility, and so on, have their own notation, their own symbology. And when those symbols exist, they should be used. But it's common to denote an arbitrary binary relation, a non-specific one, which we might denote by R, also by a symbol such as this tilde. This is the symbol I prefer to denote an arbitrary binary relation. I'm sure there are others. So now one can write this expression, A tilde B, and again you'd read it as A related to B in place of ARB, and A not related to B would look like this. This is just a more readable notation, I think, than ARB. But if you write a binary relation as a set of ordered pairs, it would look better to write R equals this set rather than to write tilde equals this set. This is awkward and open to confusion. So the truth is that there is use for both types of notation, letters to represent relations and symbols. Finally, it's customary to use a shorthand notation. For example, A1R, A2 are A3, or here it is in the other notation, to denote the fact that A1 is related to A2 and A2 is related to A3. Or in the other notation, it looks like that. As a simple example, this set is a binary relation with domain, the set A equals 1, 2. So you look at the first components, it's either 1 or 2, and the range is AC. So in this case, 1 is related to A, 1 is related to C, 2 is related to C. So we could write that this way, and here are the non-related elements. Now we come to a really important example. It's very important to understand that in mathematics, arbitrary sets do not come automatically with a useful built-in notion of equality. So equality, as a mathematical concept, needs to be defined explicitly for all sets, if you want there to be an equality relation. You might be thinking, well, since the elements of sets are sets, there's always present the notion of equality of sets as defined by the ZF axiom of extensionality. But that's not always a useful definition of equality. So it should not be automatically assumed that that is the equality. So if one mathematician, for example, were to define a new set of mathematical objects, another mathematician might very reasonably ask him or her the question, what does it mean for two elements in your set to be equal? For many sets, of course, there's a very common notion of equality. For example, a set of rational numbers. We don't need to explain equality of rational numbers unless somebody asks specifically. It's assumed that the set Q of rational numbers has the usual equality defined on it. But that is an assumption. To illustrate the reason that equality has to be defined explicitly, consider this set. This is the set of all expressions A over B, where A and B are integers and B is not 0. Now, there is a tendency to jump to a conclusion here, and that conclusion is that we're talking about rational numbers. Not so. I did not say that. All I said was consider this set of expressions. Now, if we think of these things, A over B, as simply formal expressions, so there's a top integer and a bottom integer and a horizontal line in between, and that's all we know, then as formal expressions, equality is generally defined this way. A over b equals c over d if the numerators are equal. Maybe I even shouldn't use that term, because that tends to make you think of rational number. The top symbols are equal and the bottom symbols are equal. That is a reasonable definition of equality for formal expressions of the form integer over integer. Well, if that's the case, then 1 over 2, and I can't say 1/2 because that sounds too much like a rational number. 1 over 2 is not equal to 2 over 4. Again, as formal expressions. But, as is common, we view the set A as the set of rational numbers, which strictly speaking it's not. And I'll discuss that in more detail in the chapter on equivalence relations. In fact, we'll define rational numbers, and you will see what's going on. But let's not worry about that right now. If we think of A as the set of rational numbers, which is quite common, then equality is defined as equality of rational numbers. And that is A over B equals C over D if the cross products AD equals BC. That's different from the previous definition of equality. And now we do have 1/2 equals 2/4. Okay. As another example, consider these two expressions, 1 plus x squared and x squared plus x plus 1, as formal expressions, and there are times when we want to consider them that way. These are different. They're not identical, so they're different. But as polynomials, they're equal. They're the same polynomial, but not the same formal expression. This is something you may need to think about for a while. It borders almost on the philosophical, but it is an important discussion. It's important to understand that equality, mathematical equality, is simply a special type of binary relation, and it needs to be defined. And also, you can't just take any binary relation and call it equality. As we'll see when we talk about equivalence relations, we need certain properties to hold before a relation is entitled to be referred to as equality. For example, every element must be equal to itself. We'll get into that in more detail at the appropriate time. Here's another example. If a set A has a notion of equality, if it's been defined, then we have the equality relation. This is the set of all ordered pairs AB, where A and B are in this underlying set, and A equals B. Obviously, this doesn't make sense if you haven't defined equality. This can also be written, and often is, this way. I called it delta, which is a common symbol. It's the set of all ordered pairs AA, where A is in capital A. This is generally called the diagonal relation. And so when equality has been assigned, these two are the same relation. But as somewhat of an aside, and for those who are interested in the philosophy of things, perhaps there should be a debate as to whether E and delta really are the same relation. Even if, obviously, if the issue is delta would seem to exist even before any notion of equality is defined. I don't see any equal signs in this set here. So when we write an ordered pair A comma A, are we not saying that the two components of the ordered pair are identical? Whatever that means. And that may or may not be the intended meaning of equality, or the defined meaning of equality. Equality doesn't have to be identicality. It just has to be a binary relation that satisfies certain properties that we're going to talk about in the later on, mostly in the next chapter. So we have an issue here that I don't know how to resolve, frankly, but we don't have to worry about it. For us, we'll just, once equality is defined on a set, we will take the equality relation and the diagonal relation to be the same relation. Okay. The set Z of integers has several important binary relations associated with it. As we said, there's equality and all these less than, greater than type relations. Divisibility, denoted by a vertical bar. M divides N if N is a multiple of M. If N is K times M. So, for example, 2 divides 4, but 2 does not divide 3. I don't think this is big news for you. Another relation on the integers, this is very important. We fix a positive integer k. Then we can define a relation, which I denote by r sub k because it depends on k, on the integers by specifying that m is related to n if k divides the difference in m minus n. This is equivalent to saying that m is related to n if m and n have the same remainder after division by k. So you could think of this as the same remainder relation. Nobody says that out loud, not too often anyway, but that's what it is. This is a very important relation. It has its own notation and terminology. We write m related to n this way. M, then these 3 lines, n mod k, or sometimes there's parentheses around the mod k. This is read m is congruent to n modulo, or mod k. Mod is short for modulo. So for example, 8 is congruent to 5 mod 3 because the difference, which is 3, is divisible by 3. Or another way to look at it is because the remainder in both cases, when we divide by 3, is 2. Negative 7 is congruent to negative 15 mod 4. But 6 is not congruent to 2 mod 3 because 3 does not divide the difference, which is 4. We'll discuss congruence and see more examples in the sequel. As I remarked earlier, the subset relation is a binary relation, so is the proper subset relation. And if we have statement variables in the propositional calculus, logical equivalence is a binary relation on the well-formed formulas in those variables. Here are some relations on words. We have an alphabet sigma. Sigma star is the set of all words. Remember, those are formal strings of symbols from the alphabet. This was discussed first back in chapter 6. We have the same length relation. W is related to U if the length of W equals the length of U, shorter than. Prefix relation. W is related to U if W is a prefix of U. In other words, if U starts with W and may or may not have additional symbols. Also, for example, we can pick an element, little a, out of our alphabet, and we can define a binary relation n sub a by w is related to u if w and u have the same number of a's. And we could even amend that to say the same number of a's in the same position. So there's a variety of relations that are from time to time useful on a set of words. Binary relations are just sets, of course, sets of ordered pairs. And so they are ordered by set inclusion. In particular, if R and S are binary relations, then to say that R is a subset of S is to say, of course, that every element of R is an element of an S, or put another way, an ordered pair AB is in R, implies that AB is also in S, and finally, ARB, A related to B, implies ASB. So A is R related to B implies A is S related to B. Also, because binary relations are sets, we can take their union, intersection, set difference, relative complement, and so on. And we'll talk about some of those operations later on. Binary relations on finite sets can be expressed with pictures using the concept of a directed graph, sometimes called a digraph. And that consists of a set of points, which are called vertices or nodes. So 1, 2, 3, 4 points in this graph here, four vertices, together with a set of directed lines. So here's a line from V1 to V2, and it's directed by the arrow. Directed lines are generally called arcs. So points and arcs. These are both directed graphs or digraphs. The use of the term graph here is quite different from the way you use it in calculus when you graph a function. This is a different kind of graph. As you can see, each vertex in the digraphs here are labeled for identification purposes. And we'll denote the set of vertices of a digraph by script V of D. D is the digraph. So, for example, in this figure, the vertex set is V1, V2, V3, and V4. Also, for identification purposes, the arcs are labeled. I use A1, A2, A3, A4, A5. That's not strictly speaking necessary, because since the graphs are since the arcs are directed, we can also use ordered pairs. So this arc could be identified as the ordered pair V1, V2. It's the arc that goes from V1 to V2. Now that's assuming there's only at most one arc between vertices, which is the case for our examples. So the vertex set, so the arc set for this graph here is this set of ordered pairs. That way I don't have to label the arcs. There's nothing wrong with labeling the arcs, and sometimes it's better, but it's not, strictly speaking, required. If xy, if the ordered pair xy is an arc in the digraph, so we've got a directed line from x to y, then x is generally referred to as the source of the arc and y is the target of the arc. In this example, there is an arc going from V5 to itself. These are called loops. And so the ordered pair would be V5, V5. a directed path from one vertex v1 to another vertex vk, could be the same vertex, in a digraph is a sequence of arcs. They're chained together. So it starts at v1, ends at vk. This would be the arc from v1 to v2, and would have to be followed by an arc from v2 to somewhere, v3. v3 would then go to v4, and so on, until you finally get to vk. So again, in this first example, v1 to v2 to v3 to v4, and we have a path from v1 to that one's 3, sorry, v1 to v2 to v4 to v3. That's a path. Ordered pair v1, v2, followed by ordered pair v2, v4, followed by ordered pair v4, v3. Or using the symbols of the arcs, A1 followed by A2 followed by A3. That is a directed path. V1 to V2 to V3 is not a directed path because this is pointing in the wrong direction. Just think of an ant crawling along these lines, and it's smart enough to know it has to follow the arrows, and you can trace out the paths. The length of a path is the number of arcs in the path. Okay, so that's a brief look at digraphs. This is directed graphs as a big area of combinatorics. In fact, there's a whole branch of mathematics known as graph theory. And some would consider it part of combinatorics, some would consider it a sister branch of mathematics. But there are mathematicians who specialize in just graph theory. In fact, I was one of those for a while. And it's all about the study of graphs, directed or not directed, depending on whether they're arrows at the arcs. There are whole books, many books written on graph theory. Since the arcs of a directed graph D are denoted by ordered pairs, they form a relation on the vertex set of D. And conversely, any binary relation R on a set A can be represented by a directed graph. And that's defined by taking the vertices of D to be the elements of the set A and letting the ordered pair UV be an arc of D if and only if U is related to V. And so we call that directed graph the graph of the relation. Example, equality, the diagonal relation on this set of integers can be described by this digraph. So we have the 4 elements of the set, those are the 4 vertices, and equality, the equality relation is described by the loops. Every element is equal to itself, but not equal to any other members. The subset relation on this set, just consisting of 2 elements A, B, is shown here. We have the 4 subsets, empty set, set containing A, set containing B, and the whole set, S. And we have loops because every subset is equal to itself. And we also have these arrows indicating the subset relation. So for example, the empty set is a subset of all 3 of the other subsets. So there's arrows going up, pointing in that direction. And the set containing A is a subset of the set containing AB, so we've got an arc from A to AB. the divisibility relation on the set of integers from 1 to 6 looks like this. Kind of an interesting picture. 1 divides everything, divides itself, it divides 6, it divides 2, it divides 3, it divides 4, it divides 5. So there are all these arrows. 2 divides itself, it also divides 6. It does not divide 3, so there's no arc from 2 to 3, and so on. It would take a few minutes to assemble this picture, but it's all a matter of deciding which integers in this set divide which other integers. Not forgetting that an integer divides itself. If R is a relation from A to B, we can define a relation from B to A, denoted by R inverse, and call the inverse of R simply by reversing the roles of A and B. So A is related to B by R inverse if and only if B is related to A. Another way to write the inverse is as the set of ordered pairs AB for which the reverse ordered pair BA belongs to the original relation. We can get the graph of R inverse from the graph of R just by reversing the direction of all the arcs, all the arrows labeling the arcs. Some examples, since a set A is a subset of a set B if and only if B is a superset of A, the inverse of the subset relation is the superset relation. On the family of words over an alphabet, the inverse of the shorter than relation is the longer than relation. The same length relation is its own inverse. For the set of all statements in the propositional calculus, logical equivalence is also equal to its own inverse. If A is logically equivalent to B, then B is logically equivalent to A. Let's take a look now at the composition of binary relations. If R and S are binary relations, then the composition S composed with R is defined as follows. A is related to C under the composition S composed with R if and only if there exists a B for which ARB and BSC. So this is like a little chain, A to B to C. A is related to B by R, and B is related to C by S. Some examples. Composition of congruence mod 3 and congruence mod 5. Oh, by the way, as you know from composition of functions, composition is not commutative, so S composed with R is different from R composed with S in general. Okay. So for this composition, we apply the definition. There exists an integer B such that A is congruent to B mod 3 and B is congruent to C mod 5. To untangle this, we apply the definition of congruence. So there exists an integer B such that 3 divides B minus A and 5 divides C minus B. And this is equivalent to the existence of an integer B for which there are two integers, J and K, such that B minus A is 3J and C minus B is 5K. So this is just the definition of divisibility. And this is equivalent to a little rearrangement here where I solved for b in both of these cases. So this says there exists an integer b such that b is of this form, a plus 3j for some integer j, and b is also of the form c minus 5k for some integer k. Well, that's going to be true if and only if these two expressions are equal. Then you can set b equal to this common expression. This holds if and only if this holds. I just rearranged a little algebra here. C minus a is equal to 3j plus 5k for some integers j and k. So what are the chances that that's true? Well, 3 and 5 are relatively prime. And as soon as you realize that, your brain should automatically go to Bezos Identity. I didn't call it Bezos Identity here, and oftentimes you will not see the word Bezos, but there exist integers alpha and beta for which 3 alpha plus 5 beta equals 1. This is Bezos Identity. It's just not always identified as such if you look at other books. And therefore, given integers a and c, any integers a and c, c minus a is c minus a times 1, which can be scrambled this way. This is 3 times an integer plus 5 times an integer, exactly this form. So this tells us that for any integers a and c, we have a related to c under this composition. So this composition, this relation, is what you might call the full relation. Every integer is related to every other integer. So it is in fact all of z cross z. Every ordered pair of integers belongs to this relation. And what's critical here is that 3 and 5 are relatively prime. Let's look at another very similar example where the moduli are not relatively prime. So the composition of congruence mod 2 with congruence mod 4. The algebra is pretty much the same with the obvious changes until you get down to here. And so we get this equation this time. Instead of a 3 and a 5, we have a 2 and a 4. Now, any integer can be written in this form. This is 1 times j plus 2 times k, because 1 and 2 are relatively prime. So the same reasoning, Bezos Identity, tells us that any integer has this form. Because 1 has this form, you just multiply by whatever integer you have in mind, it will still have this form, because that integer gets absorbed into the j and the k. So it's still 1 times some integer plus 2 times some integer. Therefore, if this represents, as j and k range over the integers, this picks up every integer. When you double it, you're going to pick up every even integer. So this holds if and only if c minus a is even. In other words, a is related to c if and only if c minus a is even. So that is congruence mod 2. So what happened then was this composition is just congruence mod 2. The 4 got absorbed. Congruence mod 4. One more you could try for yourself. In this case that I picked, 2 divides 4, and 4 is actually a power of 2. Maybe it would be more interesting to try 4 and 6. So they're not relatively prime, but there is another prime factor in 6, namely 3. See what you get when you try that one. Here's another example. The composition of the relation less than on the integers and congruence mod 5 would look like this. I don't know why anybody would want to do this, but it's a good example anyway. And this holds if and only if, again. There exists an integer b such that a is less than b and b is congruent to c mod 5. So you'll have to ponder this until you get an idea of what to do here. But if you have any integers a and c, you can always take b to be c plus some multiple of 5 big enough to make sure that b is bigger than a. Just kick up k until c plus 5k is bigger than a. But at the same time, then b will be congruent to c mod 5. That's why I picked a 5 here, 5k, to match the modulus here. So this too, this composition, is everything. All integers are related to all other integers.